Okay, folks, welcome back. Today, we're going to introduce the transistor. Of course, the transistor is probably the electronic element that has revolutionized the way we live the most. The computer that you're using now to watch this lecture has billions of transistors in it. Every integrated circuit has tons of these transistors. So basically, our modern life, a modern economy is based on the transistor, and it's not even an exaggeration to say that. So at the end of the course, we finally get to the transistor and how it works. So the transistor symbol in a circuit oftentimes looks like this. So this is what we'll call a bipolar junction transistor, and that's where we're going to start. There's multiple different kinds of transistors, but this is sort of the most common and basic one, the bipolar transistor. And what it has is a base here labeled B, a collector C, and an emitter E. And then here is sort of the symbol for the transistor. So right off the bat, you see that the transistor is an element that has three ports, a three-port circuit element. Okay, so what is it? Well, it is an NPN sandwich. That's basically what it is. You have an n-doped semiconductor here, n-type semiconductor. Then there is a layer here of p-type, and then there's another bottom piece here, n-type again. Okay, so that's basically in a nutshell what this bipolar junction transistor is. Now, you also get them in the other flavor, the PNP, but we'd like to discuss this NPN, and then the other one is it basically follows in a similar way. Okay, so what we can say is that this combination here, this sandwich, is sort of can be thought of as an NP junction here on top of a PN junction here. So it can sort of divide it up into NP and and then PN. All right. So here it is again. Okay, so the emitter here, okay, is the N-type. Here's the base, and here's the collector. Okay, and if you had to draw a band structure diagram, well, it would look something like this. We know that the P side is always higher in electron energy, right, than the N. That's because we have these depletion layers here and an electric field in there as well. Okay, and that electric field raises up the P, as we said. Okay, so if we have something like this and do nothing to it, this sort of would be maybe our band structure diagram, right? So just to remind you real quickly, the N-type, right, we have some donor levels, so a little bit of the conduction band is populated by electrons due to the donor levels. Of course, the entire valence band is filled, same on this side. Here, we get some holes due to the acceptor levels, okay? And of course, the conduction band is entirely empty there. So nothing new here. The Fermi energy in equilibrium is just constant, okay? And so here's the question for you. If we wanted electrons to flow from the emitter to the collector, how would we have to hook up a battery to this? Okay, so you kind of would like to now have electrons flow through this transistor from left to right. How would we have to attach a battery to this transistor? So really not a trick question here, right? How do you hook up a battery? Well, you want to get current flowing in this direction through, not current, but electrons flowing from E to C. Well, it's very clear. We have to make E, the negative, connected to the negative terminal of the battery, and C the positive. So I would do something like this, right? We would have to bias the collector positively relative to the emitter, okay, right there. So this is just common sense, really. So the thing, though, is that we can access this middle layer as well. We call it the base. We can access that too. We have another choice to make, namely, what is the base voltage? Okay, but if we do nothing, okay, other than what's shown here, you might say, all right, on the left here, in this junction, we have forward bias, right? The N side is negative compared to the P side, okay, because it's directly hooked up to the negative side of the battery. Okay, so that's got to be forward bias. But over here, we'd say it's reverse biased, right? Because the N here is connected on that side to the positive terminal of the battery. So in your mind, you might have an objection now. Can this really conduct electrons through there if we have forward bias here but reverse bias there? Okay, so let's look at that. The objection might be, will the second reverse bias between the base and the collector junction, those two, will that not block the current because it's reverse biased? Okay, so that is obviously an objection that we have to take seriously, because we've said in the past that a diode that's reverse biased doesn't conduct electricity. And so the answer is, in this case, no, it won't block the current. It actually will not block the current. So normally, of course, yes, it would block the current, but not in this context. And so we have to explain that a little bit. Okay, and in particular, we have to go back to the reason that reverse bias of a diode yields no current or very little current. We have to contend with a small drift current all the time, right? And so that is sort of the residual current that you get when you reverse bias a diode. So, but other than that, we get basically no current. So why is that, though? We said that the upshot is that there are just no mobile electrons or holes available that could support a current in this reverse bias. Okay, so there are no conduction electrons on the P side, and there are no holes on the N side, and so there's nothing to flow. That's the normal explanation. But what's different now is that we get some electrons injected from the emitter into the base. Okay, and so that is what's different now. So let's take a look at it. This is our situation now, but it's no longer symmetric. I have put this voltage there, okay, between the emitter and the collector. In other words, the collector is hooked up to the positive end of the battery, and so we drop down in energy as far as all these levels are concerned. All these bands are dropping down. Okay, so you have a picture like this now, a band structure picture. Okay, and so it looks very much like before, but I've introduced this asymmetry because we're biasing the transistor. Okay, and so so this is sort of the reverse bias here, and this might be slightly forward biased here. Okay, so we basically hooked up the collector to the positive end of the battery, the positive terminal of the battery. So what can happen now is that we're getting these electrons, and they can roll downhill. Where are these electrons coming from? Oh, they're coming from the emitter. Right, so what I'm trying to say is this in isolation wouldn't conduct, right? There wouldn't be any conduction in this picture in isolation, but now we're injecting these electrons, and these electrons are very happy to roll downhill, as always, right? They're very happy to roll downhill. So, and they're rolling downhill because we've introduced this voltage, this potential difference between the emitter and the collector. We call it V sub EC, the voltage between the emitter and the collector. And we want this voltage to be positive so that the electrons can flow. As we said in the very beginning, we wanted that to be a positive voltage. Okay, so there's another voltage here, okay, namely this little step here. It also appears down here as well, so I could have brought it in here as well, but this step here, this step up here, and we could call that the voltage between the base and the emitter, V sub BE, okay? So the question to you now is, what can we do with that voltage, V sub BE? What do you think we could do with that? Okay, the answer is we can control or modulate the current flowing through the transistor. Right, that step here controls how many electrons even get injected into the base from the emitter. And so we can actually here cut off the current entirely if we bring that base high in energy. We can bring the base back down and then really get a lot of current flowing into the base and then downhill into the collector. Okay, so this is an important point here. By modulating that base voltage a little bit up and down, we can control a large current from the emitter to the collector, or from the collector to the emitter. Okay. So a small voltage can control a large current. Okay, so that's interesting. Okay, it's very interesting. We have the possibility of amplification. Something small controls something big. We can amplify, right? There's also the possibility of an electronic switch, right? So when we bring up the base energy, we put a voltage there and we bring up the middle section in energy, and maybe maybe the switch is open, the electronic switch is open. There's no current that can flow then, no electrons that can flow from emitter to collector. And then as we bring the energy of the base back down, then then current can flow again. So we have sort of an electronic switch perhaps there as well. So it seems like it's pretty exciting, the possibilities we get with this NPN structure. Seems like there's a lot of potential applications. Okay. So let's take a look at an actual circuit. Okay, and here is sort of very simple transistor circuit. I mean, it doesn't look simple, but it's still, as far as transistor circuits are concerned, pretty simple. And of course, the transistor itself here is drawn in red. Okay, and you have the base, collector, and emitter as shown here. So here's another thing quickly that I might point out is that current flows from the collector to the emitter, but electrons, from the point of view of the electrons, they would flow in the opposite direction, right, from the emitter to the collector, and therefore these labels actually kind of make some sense from the point of view of the electron, right? They get sort of funneled through the emitter into the collector. Okay, so sort of maybe an audio amplifier that we've built here. But before we look at how this works, this circuit, let's just see if we've hooked it up correctly. Okay, so we said that the collector has to be at a more positive voltage than the emitter, right? This V sub CE has to be positive. The collector gets connected to the positive terminal of the battery, and the emitter to the negative. So is this actually the case here? Take a look at it and see what you think. Okay, I'm claiming yes, because we've hooked the collector up basically via this resistor to the 12-volt power supply, 12-volt battery power supply. Okay, but the emitter side is basically hooked up via this other resistor to ground, so 0 volts, right? And so we do get this large positive voltage. The voltage difference between C and E, of course, still will depend on how much current flows through here, right? Because we get this voltage drop across this 10K resistor, 10 kilo ohm resistor. So, okay. And then the other question I have for you is to think about what a voltage the base is kept at. Okay, at what voltage is the base kept? And so you might want to, in order to answer that, you might want to first ignore this piece of the circuit here and just look at this voltage divider here. Okay, so ignore, like, assume that maybe we have a switch here and that switch in this line is open right now. Okay, at what voltage would you find B? Well, you might recognize this as a voltage divider. Okay. And a quick calculation would reveal that that point then is at 1.1 volts. Remember, we have 2 resistors, but one is 10 times larger than the other. This is at 100 kilo ohms. This is at 10 kilo ohms. That forces this voltage here to be at 1.1 volts. Okay, so that's what we're getting coming into B, or that's the voltage at the base. Okay, so is that good? Is that bad? How should we interpret that? What does that mean? Okay, so let's take a look at the base and emitter junction. Okay, so here is just the lower piece of the base and the emitter. Okay, and so we have basically maybe this situation where the base, which is the P, is at 1.1 volts, and then the N here is via a resistor connected to ground. So if, in the case where there's very little current flowing, then you get something like this, wouldn't you? Okay, so is that, what is that? Is that forward bias? Is that reverse bias? Here we have the base basically at 1.1 volts and the emitter here via a resistor, you know, connected to ground, which is 0 volts. Is that forward bias? That reverse bias? Okay. Well, we can say that normally the PN junction, if we just leave it alone entirely, has a voltage difference between the P and the N of about 0.6 volts for silicon, we said. Right, so that's just because of the depletion layer that develops in between, at the interface between P and N. So now we're raising it to 1.1 volts, and notice that the P side is connected to the positive and the N is connected to the negative. And so we're clearly forward biased here, right? So we're in the forward biased scenario. And so the electrons should be able to flow across that junction. Yeah, they should be able to flow from the emitter to the base. Okay. But then once those electrons are in the base, what happens to them next? Well, they will get massively accelerated now as they're heading into the collector, right? So as soon as they sort of migrate over to the depletion layer between the base and the collector, they're going to be accelerated by a massive electric field, because we have that in the reverse biased situation. And so this is what would happen to them, right? Now they're in the base and they roll downhill and pick up speed, okay, and arrive at the collector. So this is sort of akin to the drift current, isn't it? But now here we're not relying on thermal excitation into the base conduction band. Okay, here we're actually injecting these electrons from the emitter. Okay, so Here's our picture again, just like before. Okay, we have these two independent voltages. Okay, and we get, if this is forward biased here between E and B, we get this diffusion current, just like in a regular diode. Okay, so this is the diffusion current, and then down here, this is sort of akin to, or very much like, a drift current. Okay, and so these electrons are going into the base, and then boom, they're getting accelerated. Okay, and they arrive at the collector with a fairly high speed. Okay, and so a couple of remarks. So that's sort of the picture that's now emerging. Okay, so that's sort of the basic idea about these transistors. So now allow me a couple of remarks to just refine the picture a little bit more. The first remark is that the number of electrons that go into the base from the emitter, okay, is roughly the same as the numbers that then go from the base to the collector. So this is sort of one stream here. Now I'm saying roughly because there might be some electrons that sort of get injected into the base from the outside, from the rest of the circuit, but more or less we can say that these electrons, okay, that go into the base from the emitter, then all of those get funneled to the collector, and so there's the numbers are about the same, okay, very close to being the same. However, we can say that the electrons arriving at C have more kinetic energy since they were accelerated by a strong electric field, right? The strong electric field in the depletion layer between the base and the collector. That electric field having been enhanced by the reverse bias, right? So we get this very strong electric field that accelerates the electrons. And by the time they get into the collector, then they've picked up a lot of speed, you could say. So there's a possibility of power amplification right there. Okay, so it's not a passive element. This is what people in electronics would call an active element. Power is not conserved. Here, we can actually get more power out than what was coming in. And so another point to keep in mind here is that the voltage of the base controls the overall current. We said this before, right? So for instance, a negative or even a zero voltage between the base and the emitter means that no electrons flow from the emitter into the base. So we can actually pinch off that current entirely, okay, if we keep the base at the same voltage as the emitter, or even at a lower voltage as the emitter, because then we would even reverse bias that first junction. Okay, so we can completely shut off that current by, for instance, having no bias between base and emitter. If that voltage is zero, then, or negative even worse, right? Or negative, then there's definitely no current. And furthermore, so the current then flows through that transistor is very sensitive to this particular voltage, this control voltage V sub BE. Okay, and so we can say that a small oscillation in V sub BE can cause a large oscillation in the overall current. So we can go back quickly to our earlier circuit and discuss this idea just a little bit more. Okay, so here it was our earlier circuit, an audio amplifier. Okay, so we decided earlier to ignore this piece, but now we'll bring it back. So this junction, if this is not here, if this AC source is not here, then this point right there we said was going to be at 1.1 volts, and forward biasing this B to E junction. And so that's good because current can flow. But now add in this AC source. So that's going to modulate this point up and down from 1.1. Okay, so small oscillations. So maybe it'll dip down, I don't know, down to 0.5 or 0.4. Okay, Maybe not as dramatic. Maybe it varies from, I don't know, 0.7 to 1.5. Okay, maybe you get some oscillations between in that range from 0.7 to 1.5. Okay, with this AC source. So this could be audio, right, coming into the mic or something. Here's a capacitor that makes sure that there's no DC offset there. Fine. Okay, now we see that this oscillation here, this voltage might oscillate a little bit at B, right? And so if I had to draw that now, so what is that voltage here? Oops. Okay. Well, before it was sort of sitting at 1.1. So maybe before it was sitting at 1.1, but now we get these oscillations about 1.1 volts. Okay, and so this V sub BE is also going to modulate. Okay, so then of course this current here is going to feel a big effect from that, in particular the current going down from C to E. So this is the positive current, right? Of course, electrons flow from the emitter to the collector, but now we can talk about a positive current, namely. Okay, and so it would flow down from the 12-volt power supply down to ground. Okay, and so, but how much current flows is going to depend on this bias here. Okay, this voltage here. Okay, and because this voltage difference between the base and the emitter is what controls how many electrons get injected into the base in the first place from the emitter, right? And so this here now has a dramatic effect on the current. Okay, and so think about this current now. It goes across a 10 kilo ohm resistor, and so if that current changes, then that voltage changes quite a bit too. Why? Because that voltage across that resistor is I times R, right? And so this current here is very strongly affected, okay, by this voltage, small voltage signal here. If the voltage is 1.5 here, then there's a lot of current flowing. If the voltage at this point in time is, say, 0.7 or something volts, then there's only a little bit of current flowing. And so then, of course, the voltage can swing quite dramatically because we have a fairly large resistor here. Okay, and so we can then power this speaker. So that is sort of the idea. A small signal here at the base can control a big voltage signal here. Okay, so very simple audio amplifier. Okay, now back to our present slide. Okay, so that is what I mean here by a small oscillation in this voltage can cause a large oscillation in the current, and then you can convert that large oscillation into a voltage again to drive the next device. So we can say that another consideration here, just as part of my remarks, okay, is that we don't want to sort of lose electrons in the base, which is p-doped, right? The p-type semiconductor via electron hole recombination. We really want these electrons to just continue into the collector. And so what we're going to do is we're going to have a thin p layer there to begin with. So we're going to engineer it such that the thickness of that p-type semiconductor is small. Okay, and then we also have a sort of fairly light p doping as well, so that there aren't that many holes around to recombine. Okay, so that's another consideration. But back to our transistor amplifier circuit one more time. Okay, so we have this piece of it here, and we can say that we're basically dealing with this current here that we want. Okay, this current could be fairly large. And then there might have to be a little bit of a current flowing into the base because the base is at higher voltage compared to the emitter. Okay, there's a little bit of current flowing in, but this is a small signal, we said, right? And so Then, of course, current. I guess this is maybe one of the Kirchhoff laws, right? So then we have to here down here we'd have the sum of those two currents. But just to quantify this a little bit, this current here up here is related via this tiny current here in the bipolar transistor via this constant beta, and the beta is on the order of 100. Okay, so this basically justifies me saying that this is a small signal, this is a large signal, right? And therefore, in the end, we might have 1.01 I sub c. So if this is I sub c, then here we might have 1.01 I sub c. So it's fairly much just, it's still justified maybe to say that these two currents are roughly the same, but maybe not exactly identical. Okay. The important point, and this is the take-home message here about transistors, is that a small current or a small voltage at the base controls a large current from the collector to the emitter, or a big flow of electrons up from the emitter to the collector. Remember, that's one complication, that the electrons always flow against the current. Okay? But that's basically the big take-home message. The whole point of transistors, you could say, is exactly that. Okay, so see you all on Friday. Right? That's all for now. Thank you.